All right, so here's a review on the other probabilities we looked at. So this is not going to cover geometric and binomial models, just basic probabilities, a tree diagram, and random variables. So the first type of probability we looked at is when the probabilities were disjoint or mutually exclusive. Those are the same thing, they're interchangeable. When probabilities were disjoint, we could just add them together if we wanted to know a probability. So let's make sure we write down that word. Mutually exclusive is the same as disjoint. So we had the addition rule that says if two events are disjoint or mutually exclusive, the probability that A or B happens, so let's remember that this symbol, the U means or, and then the N upside down U is and. We could just add the two probabilities together. The multiplication rule says if they're independent. Independent means knowing that one thing happened doesn't affect the probability of another. So flipping a coin or rolling a die, pulling from a card of decks is not independent unless you put the cards back. So when two events are independent, we can use the multiplication rule to find the probability of A and B by multiplying those two probabilities together. So the probability of rolling a 3 and then a 3 on a die, so the probability of a 3 and 3 is just 1/6 times 1/6. So 1 over 36. We can just multiply those together. And means multiply. And or we're going to add. So if I want to find the probability of a 3 or a 4, probability of a 3 is 1/6 plus the probability of 4, which is also 1/6, so that's 2/6. We want to find the complement. Sometimes it's written A with a little c, a superscript, and sometimes it's written A with a prime, and that's 1 minus the probability of A. So what's the probability of not rolling a 3? That's 1 minus the probability of rolling a 3, which is 1 minus 1/6, 5/6. So this is a simplistic example. And we use this a lot with the binomial probabilities. Probability of at least 1 is 1 minus probability of none. We're using the complement rule, so our calculations are not as complicated. The next thing we looked at was when they're not disjoint or they are not independent. Those probabilities changes slightly. The conditional probability is a probability that takes into account a given outcome. So what's the probability of A given B has already happened? When they're independent, those probabilities are going to be equal. The probability of A is equal to the probability of A given B. But when it's not, so for example, what is the probability of a 5 given the card is red? Well, your probability is different because there's only 26 red cards instead of the 52, and that changes your probabilities. Sometimes we have to use our conditional probability formula. That's here. The probability of B given A is equal to the probability of A and B divided by the probability of A. So notice that the given information is what goes in the denominator. So we say what's the probability of a heart given it's a red card? Well, there's 26 red cards and there is 13 of those are hearts. So 13 of those are hearts, so that probability is 1/2. Our general addition rule says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. The reason we have to subtract this off is because we end up counting the we end up counting the cards that are both, or the things that are both, twice if we don't subtract that off. So for example, what is the probability of a king or a spade? So a king or a spade. So this, according to our formula, is the probability of a king, which is 4 out of 52, plus the probability of a spade, which is 13 out of 52, minus the probability that a card is a king and a spade, which is 1 out of 52. There's only one king that's a spade. Minus 1 out of 52, because that card is counted in the group of spades and the group of kings. So you have to subtract that off. And that answer ends up being 17 minus 1, 16 out of 52, which reduces to 4 over 13. Our independence formula, I kind of mentioned this on the last slide, is the two events are independent if the probability of A given B has happened is the same as the probability of A happening, because what that means is knowing that B happened didn't change the probability of A happening. We want to state it in context with the proper notation when asked about independence, and sometimes we're actually doing this calculation. And then we have the general multiplication rule for two events. The probability of A and B is the probability of B times the probability of A given B has happened, or the probability of A and B is the probability of A times the probability of B given A has happened. So let's look at an example thinking about a deck of cards again. What's the probability? The probability of a king and a king. So what's the probability of getting two kings in a row? So this is the probability of getting a king. So the first king is 4 out of 52 times the probability of getting a king, given I've already gotten a king. So I no longer have 3 kings in my deck, and I no longer have 4 kings in my deck, and I no longer have 52 cards in my deck. I have 3 kings and 51 cards because one of them was taken out and not put back. And so that's how those probabilities change. The next thing we discussed in this unit was the random variables. So a random variable is not the type of variable we're used to thinking of in algebra. We don't solve equations with them. They just represent an outcome, something that's happening. We use examples like playing a game. For example, we played Greedy Pig. And if you rolled a 1, a 2, a 3, a 4, or a 6, you got that value of points. But if I rolled a 5, you got a 0. And we could create a probability model. X represents the number of points you would get. And then the probability that you get those points is the probability that X is equal to X. So in our Greedy Pig example, you had the possibility of getting 0, 1, 2, 3, 4, 5, not 5. 5 was the 0, 6 points. And the probability of each of those was the probability of rolling that particular number on the die, which is 1/6. 1/6. The expected value is how many points you are expected to earn on one given roll of the die. The expected amount you were going to win if you play a game at a carnival. That expected value is also called the mean. We find that by the sum of the x up here, times the probability, and then we add it all up. Now our shortcut to that was plugging x into list 1 and plugging your probability into list 2. And then you do 1 var stats and you look for x bar and sigma x. That is your mean and your standard deviation. Because the standard deviation calculation is much more complicated, and we don't like doing that by hand. So remember, the standard deviation describes how spread out the model is. So you're not going to earn that expected value every time. It's going to vary. You know, sometimes you'll win a lot, sometimes you'll get very little. And so that standard deviation kind of describes how much that you expect that to spread out. One thing we need to remember is that the standard deviation is the square root of the variance, or the variance is the standard deviation squared. Okay, so before we move on, let's actually look at what this standard deviation is, our mean and standard deviation here. Our expected value is 2.66, and then our standard deviation is 1.97. So, because the next thing we're going to look at is how does it change our standard deviation and our expected value if we were to change our numbers by a constant. So what does that mean, changing it by a constant? So this says the expected value, if I add or subtract a number to my values, my x's up here, then it adds that same value to my expected value. But if I add here, my variation stays the same. So we're going to do a few examples of what that means. So let's look at e of x plus 1. How does that change our table? If I add 1 to all of these points, even the 0, I get 1, 2, 3, 4, 5, and 7. Does that change my probabilities? No, it's still 1/6. And I can recalculate that expected value, and it should be the expected value plus 1, 3.66. But my standard deviation is going to be the same. So if you want, take a second and plug this into the calculator and check to make sure that is what happens. So I just did this in my calculator, and I added 1 to all of my x values in list 1. I put mine in list 3, but it doesn't matter which one. And I got this 3.66 as my expected value and 1.97 as my standard deviation. So see, my standard deviation didn't change. But how does it change if I are to multiply? So let's look at if I take my values and times them by 2. My new table looks like 0, 2, 4, 6, 8, 12. And my probabilities are the same. So what this says should happen is that I can take this expected value, 2.66, and times it by 2. So my new expected value should be 5.32. And it also multiplies my variance by 2, which in turn multiplies by standard deviation by 2. So 1.97 times 2 should be 3.94. And we'll check that. Because if I then take the square root of that, it's the same as a times standard deviation. So we get, let's see, let's take a second and put this stuff into our X list instead and see if our data matches up. Okay, hopefully you checked that in your calculator and you can see that those are the values that we got. So that's how we change it by a constant. So now what happens if we want to add them together? This represents playing the game, our greedy pig, twice instead of doubling the points. And that changes the different combinations of points you can get. So when we do that, the expected value, we can add the two expected values together. And then it's our variances that add. So our variances add together, and they always add, they never subtract. And so our formula actually ends up being very similar to our Pythagorean theorem, because the variance is sigma squared and sigma squared. So this would give you the variance of x plus y. Then you have to take the square root to get the standard deviation again. So we'll look at an example from the AP problems. Okay, so I want to look at this one first because it looks at the way our means and our standard deviations combine, and I really only want to focus on part, just finding the mean and standard deviation of the team. So the mean of the team would be the mean of runner 1. So I could take the expected value of runner 1 plus the expected value of runner 2 plus the expected value of runner 3 plus the expected value of runner 4. And when I add that up, that gives me the team expected time. Then the standard deviation is a little different. So it's the square root of the standard deviation for runner 1 plus the standard deviation for runner 2 squared plus the standard deviation for runner 3 squared plus the standard deviation of runner 4 squared. And we can do this as many times as we need to. So let's look at what that's going to be. The expected value, our mean, is going to be 4.9 plus 4.7 plus 4.5 plus 4.8. So let's add that up. Now I get 18.9 as the team mean, or expected time of the team if you were to add the scores together. And now this calculation is the square root of 0.15 squared plus 0.16 squared plus 0.14 squared plus 0.15 squared. So I just took each of these and squared it, added them up, and then I got to take the square root of it. So when I do that calculation in my calculator, I get 0.300, and that would be the standard deviation for the mean. And that's how you would find the answer to part C. This is actually part B. What I did here, what are the mean and standard deviation of the distribution for the team time? And then if I wanted to know that their best time is 18.4, what's the probability they'll beat their own best time? That's going back to using a z-score and finding that probability. You could do that by your z-score is equal to 18.4 minutes minus 18.9 divided by 0.30. So that's negative 0.5 over 0.3. And then we use normal CDF. We're talking about beating that time, which is less than, so negative 99, comma, negative 5/3. Let's see. When we do that in our calculator, we get 0.048. So the probability of them beating their best time to date is pretty low. Okay, so we did this one in class, but it's a great example of how to set up a probability distribution table when you're not given it. So 2 antibiotics are available as treatment for a common infection in children. Antibiotic A is known to effectively cure the infection 60% of the time. Treatment with antibiotic A costs $50. Antibiotic B is known to effectively cure the infection 90% of the time. Treatment with antibiotic B costs $80. The antibiotics work independently of one another. Both antibiotics can be safely administered to children. A health insurance company intends to recommend one of the two following plans for treatment for children with this ear infection. So plan 1, they treat with antibiotic A first, and if it's not effective, then they treat with antibiotic B. Plan 2, they treat with antibiotic B first, and then if that's not effective, they use antibiotic A. If the doctor treats a child with an ear infection using plan 1, what's the probability the child will be cured? If the doctor treats the child with an ear infection using plan 2, what is the probability that the child will be cured? So the probability that a child is cured with plan 1 is the probability that antibiotic A works. That's the first thing, right? And then the probability that they have to use antibiotic B is the probability that A did not work and B did work. which is the probability that A did not work and B does work. And because they're independent, that's the probability that A does not work times the probability that B does work. So this problem uses a lot of the other probability ideas as well. So the probability that A worked is 0.6 plus the probability that it didn't work is 0.4. Because in order for them to need to do part B, or antibiotic B, the first treatment didn't work, times the probability that B does work, which is 0.9. And that's 0.6 plus 0.36, which is 0.96. So the probability that plan A cures the kid is 0.96. So plan 2 is the probability that B works plus probability that B does not work and A does work. So the probability that B works is 0.9 plus the probability that B does not work, 0.1, times the probability that A does work, 0.6, which is 0.9, plus 0.06, which is 0.96. So what we've learned is the probability of getting a cure is the same for both plans. So compute the expected cost per child when Plan 1 is used for treatment, and compute the expected cost per child when Plan 2 is used for treatment. So now we have to set up a probability table. So this was A, and this is B. We'll start it over here. So this is Plan 1. It is going to cost them $50, and the probability that it costs them $50 is 0.6, because if they're starting with cure A, antibiotic A, which costs $50, if it works the first time, that probability is 60%. Now the probability that they have to use B is 0.4, and that actual cost is going to be $50 plus the $80, so it's going to cost them $130, 0.4% of the time, because they're administering this drug first and it didn't work. So they've already paid for this drug and now they have to pay for antibiotic B as well. So that cost them $130. And that expected value is 50 times 0.6 plus 130 times 0.4. Sometimes it is faster to do it by hand. So Plan 1's expected value is $82. So our expected value of Plan 1. Now looking at Plan 2, it's going to cost them at first $80. And that has a 90% chance of it costing them only $80. And then it's $130 if antibiotic B didn't work and they have to give antibiotic 1, and that's 0.1. Now remember that a probability distribution, they have to add to 1. So I'm not looking at the fact that this worked being 0.36. I'm just saying if this was administered and then we had to go to this treatment, it's going to be 0.4. The kid still might not be cured after those 2 treatments, but that's not a part of our problem here. So this expected value is 80 times 0.9 plus 130 times 0.1. And so this is $85. And so part C, we have 2 expected values here, 85 and 82. Based on the results in part A and B, which plan would you recommend? So at this point, because the probability of curing the kid is the same no matter which plan you use, you would recommend Plan A or Plan 1 because it is cheaper. Now to us, $3 is not a big deal, but when you're talking about an insurance company that has hundreds and thousands of patients, then $3 becomes a lot of money. All right, so the last thing I have is I found some multiple choice questions we can look at on probability. The probability of A is 0.7. Probability not B is 0.4. The probability of A and B is 0.5. find the probability of A or B. So first of all, if probability of not B is 0.4, what is the probability of B? They're trying to trick you here. 0.6. So then we have our formula, the probability of A or B, oops, that's an and, or B is equal to the probability of A plus probability of B minus the probability of A and B. So this is 0.7 plus 0.6 minus 0.5 is 1.3 minus 0.5, which is 0.8. C. Of the registered voters in a community, 58% are female. A local politician running for office has the support of 48% of the registered women and 53% of the registered men. What percentage of the vote can the politician expect to get? So the population is 58% women and 42% male. And the support is 48% women and 53% men. So we can expect him to get 48% of those 58%. So we're doing 48.48 times 0.58 plus 0.42 times 0.53. And we get 0.501, so that's 50.1% B. For the given probability distribution, find the standard deviation of X. So to do this, again, we're going to enter this data into list 1, any list you want really, and this data in list 2. And then when you do the 1var stats, if you have the old calculator like I do, you're going to do list 1 comma list 2. If you have the new one, you're going to put list 2 under the frequency. And then the I don't know what it says, but you put the L2 in the other, and the L1 in the other one. And then you just look for sigma x. So let's see what we get. So when I did that in my calculator, I got 2.621, which is B. And our last example is home pregnancy test kits have grown in popularity. Research shows that only 30% of those using the kit are actually pregnant. So the probability that a woman is actually pregnant if they're taking the test is 0.3. When a pregnant woman uses this kit correctly, it correctly indicates pregnancy 96% of the time. So the probability that it says you're pregnant, let's let a P equal pregnant test, and then a negative would be not, it's saying you're not pregnant. So you get a positive given you are pregnant 0.96% of the time. And then a woman who is not pregnant gets a correct indication. So it says they're not pregnant, given they are not pregnant 0.9% of the time. So here I'm given a probability and then 2 other probabilities that are conditional. And this is when we use our tree diagram. So the first branch of our tree, and what's the probability that a woman is pregnant given that the test is positive? So what's the probability that she's pregnant given she got a positive test? Because that's what happens. You're using the test to find out if you're pregnant. So let's see. We start our branch with the probability that the person taking the test is actually pregnant is 0.3. The probability that they're not pregnant is 0.7. And now we use our conditional probabilities here. The probability that they get a positive given they are actually pregnant is 0.96. Oops, it's about 6. The probability they get a negative given they were actually pregnant is 0.04. Remember that our branches have to add to 1. The probability that they get a positive given they are not pregnant, and this one's going to be the probability that they get a negative given they are not pregnant. So we'll put this one in first. That we know is 0.9, and so because they have to add to 1, this is 0.1. So when I multiply those together, we know that the probability of P times the probability of a positive given P is equal to the probability of P and a positive. And the probability of P times the probability of a negative given P is the probability of P and a negative. The probability of P complement times plus given P complement is a probability of P complement and a plus. And then the last one is your probability of P complement and a negative. Now we multiply those together. We get 0.3 times 0.96, which is 0.288. And this is the 0.3 times 0.04, which is 0.012. This is the 0.7 times 0.1, which gives me 0.07. And this probability is 0.7 times 0.9, which is 0.63. So now we can go back to what it's asking us. What is the probability of P given a positive? And use our probability formula to say that is equal to the probability of P and a positive divided by the probability of a positive. Now the probability of a positive will include being pregnant and getting a positive and not being pregnant and getting a positive. So the probability of a positive is 0.288 plus 0.07, which is 0.358. So that goes in our denominator, 0.358, and our numerator is the 0.288. When I do that on my calculator, 0.288 divided by 0.358, I get 0.804, which is about 80%. So that means the probability that you are actually pregnant, given they get a positive result, is only 80%.